Okay. Okay, we're starting, okay? Uh, 5.3. Oh, I want you guys to do one thing. I open up, because we have a test in about a little bit over a week, on Wednesday next week. So the test will be submitted as either PDF or pictures through Canvas. So I just open up some kind of trial test. The trial test is just asking you to solve 3 times x equal to 6. I hope you all know the answer is x equal to 2. But I just want to put it there so that you can actually try out submitting it in Canvas. Okay? So I have it. The deadline I have it is submitted by tomorrow, 12:45. So please try to do it to make sure that you are able to submit it successfully. You guys understand what I'm saying?
Yeah.
Okay, good. Yeah. Just want to make sure that you get the process. You can successfully go through that process. Okay. Of course, in the actual test, you're not going to have the whole day. You're going to only have like 75 minutes or 90 minutes. Yeah, I think I'm planning on 90 minutes. Yeah. Okay, any question about that? Please go ahead and try it, okay, after the class. Okay, try to convert it to basically just write down. I mean, I'm going to post the questions and then you are going to just answer the questions. You don't have to copy the questions, okay? Number 1, number 2, number 3, and so on. Just write out the answer, show work, take picture, or convert it to PDF and submit it inside Canvas. Okay, so we are doing 5.4. 5.3, I mean. Diagonalization. Can you guys compute in your head for me mentally what will be d squared? D times d? What do you think?
15.
Will it still be a diagonal matrix, the answer?
Would it be like 25?
25, 0.
25, 0, 0, 9, right?
Yeah.
What would be d cubed? And so on. What would be d to the power k? 5 to the power k, 0, 0, 3 to the power k. All right. Okay, so now we're going to do this example. We want to do a to the power k. For this matrix, this matrix is not a diagonal matrix, okay? And so because it's not a diagonal matrix, it's not going to have that nice property, okay? But this is what we're going to do, okay? We're going to write A equal to P inverse, where P is an invertible matrix and D is a diagonal matrix. Okay. I'm going to show you how to do this, how to write A equal to PDP inverse. Okay. But I'm going to jump ahead and show you what happens if that is the case. Then AK will be PDP inverse times itself all the way here K times. Now I'm going to regroup this. What happened to P inverse times P? By the way, matrix multiplication is associative, so you can group it any way you like. You can do different brackets. Okay. So what is P inverse times P?
I.
That's I, identity. So identity times D will be gone with just D. So you will have a bunch of I's around. Another I here, some other I here. So at the end of the day, this will become P times D to the power K, P inverse. Okay, I want you to make sure that you understand what's going on there. Can you guys see this equal sign? That particular equal sign. Because all the P inverse and P cancel out each other in the middle. After you cancel out, all this D will be next to each other because DI is the same as D, right? The I is going to be gone. So it's going to be a bunch of D. How many times? K of them. Is it okay? You guys okay?
Yeah.
So now we boil down to trying to find the P. Okay, and the D. And this process is called diagonalization. I'll formalize the definition, okay? But I just want to work through the example first, okay? Here's how we do it, okay? So A is equal to 7, 2 minus 4, 1. So the process to find P and D is to find, so these are the steps, okay? These are the general steps, okay? Find eigenvalues and eigenvectors of A. Now, how do we do that? Eigenvalues and eigenvector. So you do determinant A minus lambda I equal to 0. A minus lambda I equal to 0, so will be determinant of 7 minus lambda, 1 minus lambda, 2 minus 4 equal to 0. If I make a mistake, you need to let me know. 7 minus lambda, 1 minus lambda plus 8 is equal to 0. Lambda squared minus 8 lambda plus 7 plus 8 equal to 0. Lambda squared minus 8 lambda plus 15 equal to 0. Lambda minus 3, lambda minus 5 equal to 0.
Then I was asking, how do you know that he was sitting next to you?
Is it okay? Is it all right, guys? Did I make any mistake? Are you guys able to? Okay, so lambda equal to 3 and lambda equal to 5. I think we might have looked at this problem, do this problem before the break. I forgot. Or similar, this matrix, I mean. Okay, let's do this. Lambda equal to 3. Lambda equal to 3, what happened? Lambda equal to 3 will be, we're solving this guy, subtract 3. So it will be 4 and 2 minus 4 minus 2, 0, 0. You guys with me? The diagonal subtract 3. So this one will be 1, 1/2, 0, 0, 0, 0. Okay. So V1 will be what? V1 will be negative 1/2. Are you guys able to follow? I skip a bunch of steps. But you guys will be pretty good by now. Yes or no? X2 equal to X2, X1 equal to negative half X2. Yes? Okay, very good. So I'm not going to use this one. I don't like the fraction. So I'm going to do this. I'm going to use negative 1 and 2. Is it okay?
Good.
Very good, Anna. Thank you. Lambda equal to 5. Subtract 5. 2, 2, 0, minus 4, minus 4, 0, 1, 1, 0, 0, 0, 0. V1 will be minus 1, 1. V2. Okay? Now, what we have is the following now. What we have is now A times V1 is equal to 3 times V1. A times V2 is equal to 5 times V2. Okay? That's the definition of eigenvalues and eigenvectors. So A times V1, V2 is going to be equal to, I'm going to write this in this form, 3, 0, 0, 5. V1. Okay, sorry, it's the other way. Sorry, I have to erase it. Okay, I want to convince you this equation is the same as this set of equations. Are you guys convinced or not? A times V1 is this guy 3, 0. You do this to a linear combination of V1 and V2. It's 3 times V1 plus 0 times V2. A times V2 is this linear combination. It's okay, which reduces these two equations. This is kind of the important point here. Okay. This is a key step conceptually. So now I'm going to call this matrix P. So now I have AP equal to PD, and this matrix is my D. Now D is a diagonal matrix. Okay, and now I have A is equal to PD, P inverse. So I successfully diagonalize A. Okay, so I diagonalize A. That means I write A equal to this form. So now my A to the power K, just not very good at this. Okay. So now a to the power k is p. What's my p? P is the v1 and v2 put together, right? What's my v1 and v2?
-1, -1.
Like this, right?
1, yeah.
It's okay. D to the power k. D to the power k. What is d to the power k? 3005, 3 to the power k, 5 to the power k, 0, 0. Times P inverse. What is P inverse? Inverse of that matrix. So this is P. P inverse, it will be 1 over the determinant. Determinant is what? -1 plus 2. 1 negative 1. 1 negative 2. This is my P inverse. Do you know what I did? 1 over AD minus BC. DA minus B minus C. You know what I'm doing?
Yes.
Yeah.
Okay, very good. Thank you. So 1 minus 2, 1 minus 1. So I'm nearly done. So, and here you can write this out. I have to erase it, sorry. Okay, multiply this together. Minus 3 to the power k, minus 5 to the power k, 2 times 3 to the power k, 5 to the power k, 1, 1 minus 2 minus 1. So it will be minus 3 to the power k plus 2 times 5 to the power k minus 3 to the power k plus 5 to the power k, 2 times 3 to the power k minus 2 times 5 to the power k, 2 times 3 to the power k minus 5 to the power k. Yeah, this is correct. Okay, that's my answer. If I did not make any mistake. Any question? It's kind of important. This illustrates a lot of concepts. Good. We move on. Are you guys okay?
We're still here.
Still here? Good. Thank you. I appreciate this, Anna. I know you have experience, so you know that when you teach, you want the student to say something, right?
Yeah, we want to know that they're doing, at least paying attention.
Yeah, that's right. So thank you. Did you buy your whiteboard, Anna?
No, I decided to screen share using a different program.
Okay. Okay, formal definition. Okay, that's the definition of diagonalizable. But I haven't told you what similar means. So I have to give you the definition of similar matrix. Okay. Okay. Two square matrices. Okay. Two matrix A and B are similar if A equal to P dP inverse. Okay. And a square matrix A is going to be diagonalizable if it's similar to a diagonal matrix. Hopefully you understand what this is saying. Let me know if you have questions, okay? Otherwise, I keep going. All right. Here's a result. Similar matrices have same characteristic equations. And eigenvalues. Okay. So if A and B are similar, they have the same characteristic equation, and so they have the same eigenvalues. It's actually not too difficult to see. Determinant of A minus lambda I is the same as determinant of P inverse minus lambda I, which can be written as determinant of P inverse minus P lambda I P inverse. Take the P common factor P and P minus out. And this will be determinant of B, determinant of B minus lambda I, determinant of P inverse. These are numbers now. So these are numbers, okay? Each of these is these two are numbers. This is a P. Okay? These are numbers. Okay? This is an expression. These are not determinants anymore. After you do the determinant, it's not some kind of expression. It's multiplication. So you can swap the order. So you become determinant of P, determinant of P inverse, determinant of, I'm sorry, this is just a bunch of writing. And these two here, you can combine it together. The determinant of P inverse, determinant B minus lambda I. But P times P inverse is I. and determinant I is 1. It's just a bunch of symbolic manipulation. The bottom line is that they have the same characteristic equation if they are similar matrices. It's basically the matrix is really similar in the sense that if you represent a transformation, it represents A and B both represent some kind of transformation in different coordinate system, essentially.
Can you repeat that, what you just said?
Okay, sorry.
Oh, no, not the whole thing, just that last phrase.
The last sentence,
Yeah.
I didn't really teach all the details, but what that sentence is saying that if A represents a linear transformation, right? From
Mhm.
x go to ax,
Yeah.
from x go to ax, B also represents a linear transformation, okay? From x to bx. So these are the two different, so from x going to ax is a linear transformation. From x going to bx is another linear transformation. So these are essentially represent the same linear transformation, except it's a change of coordinate system. If you do some type of substitution, you will get one matrix to the other. I'm going to be able to illustrate this on a later section, Eva. I'm going to illustrate this again when I get to a later section.
Okay. I have another question. How are you allowed to make determinant of P inverse minus lambda I to determinant of P inverse minus P lambda I P inverse?
You mean this equal sign or which one?
No, the one
The
two
first
above. Yeah, that one. How did you?
From here to here?
Yeah.
Here. Okay, because what I'm really saying is that this guy is the same as this guy, right? That's what I'm saying.
How or why can you do that?
Why can I do that? Because this lambda is a constant. You can take it out. Take the constant lambda out to the front. Okay?
Okay.
And then P times I is equal to P. And P times P inverse is equal to I.
Okay, thanks.
Okay?
Yeah, thanks.
I'll try to get back to this, okay, Eva, later on. Okay?
Okay, thanks.
Okay, so the main thing, I mean, this result is kind of interesting, but then we don't really use it a lot. But I mean, the main thing is that you need to know that, I mean, similar matrix have same eigenvalues and eigenvectors, same characteristics equation. But the main thing for this section is really this process in some sense, okay? Okay. So let's do another example. Okay. Let's do another example. The way that this question is worded, diagonalize this matrix is possible. That means sometimes it's not possible. Okay, we'll talk about under what condition it's not possible a little bit later. Okay, we'll try. I mean, if you get stuck, then it's not possible. Okay, We will talk about that in a little bit more as we keep going today. So based on the earlier example we did, so what's the process to diagonalize a matrix? We need to find eigenvalues and eigenvector, right? The eigenvalues, so basically find eigenvalues and eigenvectors. So the eigenvectors, this guy will give you the matrix P, and this guy will give you the matrix D. Okay? So in order to do that, okay, let's do this. A determinant A minus lambda I equal to 0. It's a little bit ugly, guys. Do you want me to come, because it's a cubic, it's a little bit ugly? We can do that. One way is to save some time. Can I save some time by just writing the characteristic equation?
Yeah.
Okay, it will save some time, okay? So it end up, this guy will be minus lambda minus 1, lambda plus 2 squared equal to 0. It's a cubic, it's ugly, okay? Cubic sometimes is difficult to factorize, but this case is, you can do it. Okay, so what do we end up with? Lambda is equal to 1 and negative 2 twice, right?
Yeah.
Right?
Yeah.
So the algebraic multiplicity of this guy is 1 and this one is 2. Okay? So let's do lambda equal to 1. Lambda equal to 1, what happened? Subtract 1 on all the stuff. Keep subtracting 1, you have 0, minus 6, 0. Let me know if I mess up.
So the negative at the beginning of
Yeah, you get rid of it by dividing it out.
just divide it out. Okay.
Yeah. Can I cheat again to save time? Can I just write down the RREF? Or you guys can type it into the calculator. Okay, so what is V1? The eigenvector. You guys will be very good at this. You may be able to just write it down right away. Can you?
There's some glare on the first entry. What is it? 1?
This one?
Oh, 1.
Is it better?
Yeah, it's a little better now.
Some glare.
Yeah.
Okay, let's see. Here. Is it better or not? Or worse?
It looks like it's the reflection of the overhead light.
It's a light bulb.
Yeah.
It's bad. Oh wait, now it's okay.
Is it better?
Yeah.
Turn off the
Yeah.
overhead light and use the outside natural light.
Yeah, that's better.
Thank you. Thank you. My wife helped me out. Yeah, I was thanking her. So better? Okay. Can you write the RV1 right away in your head? I would say this is going to be 1 minus 1. 1. x3 equal to x3, 3 variable. x2 equal to negative x3. x1 equal to x3. Is it okay?
Yep.
Yes.
Okay. Lambda equal to 2. Minus 2, sorry. Minus 2. Minus 2, this one becomes 3. Minus 2. Minus 3. Is it okay? This one I can do in my head. So how about here? This earlier one I wasn't able to do in my head. Okay, I will just copy from my earlier notes. This one, all these lines are the same. Okay, so we'll try to convince you this. X2 equal to X2, X3 equal to X3, X1 equal to negative X2, negative X3. So V2 will be minus 1, 1, 0. The next one will be minus 1, 0, 1. Is it okay?
Yes.
Okay, so my P, this is my P. It's 1 minus 1, 1, minus 1, 1, 0, 1, 0, 1. And my D, first vector, this first vector corresponds to the lambda equal to 1, so I have the lambda equal to 1 here. The other two is minus 2. So this is kind of important to make sure that they correspond correctly. Okay, the first one corresponds to the first column, second one, second column, third one, third column. Is it okay? Okay, so we're done. So the way I remember this, is that based on the definition of eigenvectors, I know that A times P, because P is all these eigenvectors put together, right? A times the eigenvector is equal to the eigenvalue. Is equal to the eigenvalue times the eigenvectors.
Where did the D matrix come from?
Come from the eigenvalues. So this become AV1 is V1, AV2 is negative 2V2, AV3 is negative 2V3. Okay, so this thing can be written as V1, V2, V3 times this 1 minus 2 minus 2. Okay, so basically this is saying what this is saying is that AP equal to PD. Okay, and of course this was the same. AP equal to PD, so you put the P to the other side, A will be PDP inverse. Is it okay? Any questions so far? So we diagonalize this matrix. So it's possible. In this case, it's possible. When is it not possible? You remember geometric multiplicity, you remember this geometric multiplicity less than equal to algebraic multiplicity? You guys remember that?
Yeah.
Okay, so a matrix, a square matrix is diagonalizable if geometric multiplicity is less than is equal to algebraic multiplicity for all eigenvalues. Okay. Another way to say this is that the dimension of the eigenspace for lambda, okay, is the same as, okay, maybe I just draw a line here. So this is the same. Dimension of the eigenspace is equal to the algebraic multiplicity of lambda for all lambda. For all eigenvalue lambda. Okay. So here in this case is 1 minus 2 minus 2, right? The minus 2 has algebraic multiplicity of -2. But luckily the geometric multiplicity is also -2. So it works out okay, otherwise it won't work. So basically, the question is that are you able to get enough linearly independent eigenvectors? Okay. So another way to say that, another way to say the same thing. Another way to say the same thing is that it's n by n square matrix. So we want to have n linearly independent eigenvectors. Okay? All these are essentially talk about the same thing. So if you have enough linearly independent eigenvectors, then it's diagonalizable, otherwise it's not. Are we kind of okay?
When the lambda is -2 for both of those eigenvectors, do they have to be linearly independent?
Yeah, they have to be linearly independent. Yeah, they have to be linearly independent because here we are looking for, in this case, we are looking for the eigenspace to have dimension 2, okay? This guy, because the multiplicity is 2, so we are looking for 2 free variables, which we do have. We have the free variables x2 and x3. Because only one of these lines is useful. So both of these are free. Okay. I'm going to give you an example where it's not the case. It's not diagonalizable.
Are eigenvectors for a given matrix, they're always linearly independent? Is that?
For distinct eigenvalues. Okay. Let me write that problem, write that down. I actually proved that. A while ago.
Yeah.
Okay, so.
Okay.
Okay, eigenvectors corresponding to distinct, that means different, eigenvalues are linearly independent. Okay. So if you have all the eigenvalues are distinct, then it's going to be okay. You know what I'm talking about?
But like for the -2, they're not distinct. Or wait,
So it's not distinct. The -2 in this case is lambda equal to 1 and -2. This is not distinct. So it may or may not work when it's not distinct. So this is just saying that if it is distinct, if all the eigenvalues are different, then it always work. Okay? But if some of them are not distinct, then it may not work, depending on the situation.
Oh, okay. So we got like lucky here, I guess.
Yeah, in some sense, got lucky.
Okay, thanks.
We're going to give you an example where you are not that lucky. Okay? You guys understand this, other people? What the point Eva was trying to make? So if you have eigenvalues are all distinct, then you're done. Because each eigenvalue you have, you can get at least one eigenvector, right? And different eigenvectors correspond to this. Different eigenvalues are going to be independent. So you will always have enough in that case. But when some of them some of the eigenvalues are repeated, then it may or may not work, as shown by the next example. Okay, so maybe I just also write down here. Eigenvectors correspond to distinct eigenvalues are linearly independent. And n by n matrix with n distinct eigenvalues is it going to be diagonalizable? Can we guarantee that? We can, right? That will always be diagonalizable. Because n distinct eigenvalues, they are all linearly independent with each other. So that whole set of stuff will be able to use it to find your matrix P. Okay, so what do we do again? What is the procedure?
So we have to find the eigenvectors and the eigenvalues so that we can get our D and our P.
That's right. Very good. So A minus lambda I. So determinant. We're going to compute the determinant here, okay? Because this one is not too bad. It's okay? Lambda equal to 1 and 1. Geometric algebraic multiplicity is 2. So we do this, we try to do, we're going to try to find 2 linearly independent eigenvectors. Okay, lambda equal to 1, so it's 1 minus 1, 1 minus 1, 0, 0. This would become 1 minus 1, 0, 0. Are there enough free variables? There will be one, in this case, there's 1 free variables, right? So V1 will be 1, 1. Do I have another one? I don't. I only have 1 free variable. Is it okay?
Yes.
Okay, so is it diagonalizable or not?
No.
A is not. You guys doing okay?
Yes.
This section is kind of fun. Hey, what do you think the answer to this is? You guys have an answer for me on this? Can you look at that matrix and find out the eigenvalues?
5, 0, -2.
Okay. Are they all distinct?
Yes.
There are no repeated ones. So is it diagonalizable?
Yes.
Yes. Okay.
I have a question. Are non-n by n matrices invertible?
You mean diagonalizable? Yeah, we do only square matrix here. Is that what you're asking?
Sorry, what was that?
We only deal with square matrix.
Okay.
You say non-n by n, that means not square, right? Is that what you mean?
Yeah. So can a matrix be invertible if it's not n by n?
Invertible, no.
Okay.
Only talk about inverse when it's n by n. There are other notions of, there's something called pseudo inverse, but we are not going to talk about that. It's it's not part of this class. Pseudo inverse, Penrose inverses. I'm not going to talk about. I won't be able to talk about that.
Okay.
But we only deal with invertible ones. Invertible matrix, we only deal with square matrix. Same as diagonalizable matrix, we only talk about square ones. Okay, but there are generalization of that. Okay, pseudo inverses. Okay, how do we determine this? Do we know the eigenvalues?
Yes.
We already know that. Are they all distinct?
No.
Lambda equal to 5, 5, -3, -3. Okay? And because it's a lower triangular matrix, right? And that one was an upper triangular. Okay, so lambda equal to 5. Now lambda equal to 5, I want to get eigenspace of dimension 2. Okay? I want to have 2 free variables when I solve ax equal to 5x. So subtract 5. Subtract 5 is just a bunch of zeros, 1, 4. Subtract 5, -8. Hey, what do you think? Are there two free variables?
Yes.
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 It's two free variables. Okay? It depends on how you look at that, yeah. Two free variables. So dimension of E5 is equal to 2, which is good. So we have enough. We are happy. How about lambda equal to -3? -3. You add 3.
Explain how you know we have enough again. Like, why is 2 enough?
Say it again, Luca.
Could you explain why 2 is enough?
Or because algebraic multiplicity is equal to 2. Algebraic multiplicity is equal to 2. And geometric multiplicity is always less than or equal to that. So when you have, if you get 2, then it's good enough. If you're less than 2, then you don't have enough. Because that means here, I'm going to be able to get 2 linearly independent eigenvectors. And if I also can do the same thing down here, then I'm okay. Yeah,
and you're doing that because you have 2 5s.
Yeah, because I'm 2 5s. If I have 3 5s, I will want to have this dimension 3.
Okay.
Yes. If all 4 are 5s, I will want to have dimension 4.
Okay. Is that because you want like 2 linearly independent eigenvectors so that you have like 4 eigenvectors so that you have like the right dimensions?
Yeah.
Or...
Yeah. You need because this is 4 by 4. I want 4 linearly independent eigenvectors at the end of the day.
Okay.
So each of these has to attain its maximum possible. Okay? One for this and every single one. I erased some of this earlier, but those are the conditions right now. For all the eigenspaces, has to get to its full potential. Where the dimension is actually, the dimension of the eigenspace is called geometric multiplicity. You want the geometric multiplicity to be equal to the algebraic multiplicity. Okay, the biggest possible. Otherwise, it's not going to work because the number of roots here, this is 4 of them, right? Is equal to the dimension, is equal to the dimension of the matrix. This is a 4 by 4 matrix. We are not dealing with complex number here, so I mean, we are going to just deal with all these cases of real complex. We're not going to deal with it. You cannot have a degree 4 equation. The characteristic equation is degree 4, right? You're not going to have 5 roots. You guys understand what I'm talking about? It's called the fundamental theorem of algebra. The degree 4 equation, the degree n equation will have at most n roots.
So what determines the number of the degrees? Is it the rows or the columns?
The degree is the size of the matrix. 4 by 4 matrix will be degree 4.
Okay.
Because it's determinant of A minus lambda I, right? You subtract lambda, subtract lambda, subtract lambda, subtract lambda. Then you can follow of the lambdas multiplied together as degree 4. The characteristic equation of an n by n matrix is degree n. Yes?
Okay, got it. Yeah.
Okay, so what happened here? I add 8, right? I add 3. Oh my God, what happened? I add 3, yeah. I add 3. So this guy will be 1, 4, 0, 0, minus 1, minus 2, 0, 0. So does this work? What's the dimension of E minus 3? How many pivots are going to be here? if you do RREF of this one, this will be a 1 and a 1, and this guy will be all 0 out, right? Can you see the REF of this guy is going to be this?
Yes.
2 free variables. Is it diagonalizable or not?
Or how does the 4 cancel out?
This 4, how this going to be gone?
Yeah.
Is that what you're asking me?
Oh wait. Oh, and I
Okay,
think
okay.
never mind.
No, I'm talking about this guy is going to be able to use it to this guy's subtract 1 times this guy, right?
Oh, okay. Okay, thanks.
And then later on subtract 4 times this guy after you change it to 1. You know what I'm talking about?
Yeah.
Yeah, because you have the pivot there, things under the pivot. I mean, if you keep going, you're going to zero them out, right? Okay, so is it yes or no? The answer. Do we have enough eigenvectors?
Yes.
We have 2.
Yes.
2 plus 2
Yes.
is 4. Yes. We have enough. How are we doing, guys?
Doing all right.
A lot of terminology.
A lot of terminology, yeah. Yeah, a lot of terminology. It's kind of crazy. Oh, I'm going to remind you one more time to do that trial test. There's nothing in it, the test, okay? It's asking you to solve 3x equal to 6. You should know the answer. And the main thing is to try to submit it, okay? Take some pictures and submit it. Okay. So we have a little bit of time. So okay, I'm going to ask you this question. You guys tell me whether it's true or false. Okay. What do you think? If you think it's true, you have to explain it to me. Why is it true? If you think it's false, give me a counter example. You can think about it. We have some time. Anybody volunteer to take some guess?
No thanks.
You say no thanks, you don't want to guess, or you say the answer is?
I don't want to guess.
Okay. You can raise your hand if you think that this is true. You guys know how to raise your hand in the software? I see a couple of hands. Who think it's false? So most of you have no opinion.
Wait, oh shoot. I think it's true.
You think it's true? If you think it's true, you have to explain it. If you think it's false, you have to give a counter example.
Oh, should I explain?
Okay, yeah.
I think it's true because if it's diagonalizable, then you need four linear, or not four, like n linearly independent eigenvectors.
Yeah.
And so then, so you need that for P.
Okay.
And, oh, so I think that means A is invertible. That was kind of weak.
Okay. I'm going to go through this then. The answer is actually false. It's actually two different things. Now, if I say it's false, what do I need to do to convince people?
Counterexample?
Counterexample. So I'm looking for a matrix A that's diagonalizable. Okay. So I'm going to just say A is this. Is it diagonalizable? It's already a diagonal matrix. So this one is, so A is equal to, my P is just an identity matrix in this case. Okay. And this is my D. This is my P. So P inverse is just itself because it's an identity matrix, right? So is this matrix invertible? The determinant of this matrix is, what's the determinant of this matrix?
0.
0, yeah. So A is not invertible. Is it okay? You can even.
Is, oh, can I ask a question?
Yes.
If A is diagonalizable, does that mean it's not invertible?
No. Doesn't mean that it's not invertible. It's just completely different thing.
Okay.
So you can have A equal to this. This is definitely diagonalizable already. It's already a diagonal matrix, right? But this one is invertible. So basically, when it's diagonalizable, it can be either way. You can't really make a conclusion from the fact that it's diagonalizable whether it's invertible. It just sometimes it's easy to get mixed up with those concepts. Okay, we finished this section. Next time, we're going to use linear algebra to solve a system of differential equations on Wednesday. Okay?
All right.
Thank you.
Just wondering as well, Professor, will the things we're covering this week be on the exam next week?
Say that again.
Will the things that we're covering this week, like diagonals and stuff like that, be on the exam next week?
Yeah, I mean, I sent out the study guide as an
Oh, okay. I didn't see that.
yeah, it's up to today and also the next section.
Gotcha. Thank you.
Yeah. Okay. Anything else, guys? Make sure you try the trial test. Okay.
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 Thank
All
you.
right. I'll see you guys on Wednesday. Okay. Thank you.
Thank you.
Thank you.
Thank you.
Have a nice day, Professor.
Oh, you too. Okay. Bye bye.